Hello and welcome to the World Copper Conference panel on the future energy transition. We'll be diving into some key areas of import to the global copper industry, including how substitution of the red metal could be affecting demand, new and emerging demand from the power cable sector, and most importantly, the role and demand for copper in the future automotive market, electric vehicles, and other technologies of the future. I'm Ernest Scheyder with Reuters, and I cover the copper industry closely. I'm joined today by 4 experts from across the spectrum to share their insight and wisdom with you. We have experts from DMM Advisory Group, SAI Industrial, IDTechEx, and Frigus Bohn. And we're going to have presentations from each of them, followed by a time for Q&A. So if you do have any questions, please hold them until the end, and we'll have a live Q&A discussion. Now I'm going to turn it over to Kalman-Schueler from DMM Advisory Group.
Good afternoon to all participants of the World Copper Conference, either online or real life. My name is Kalman-Schueler of DMM Advisory Group, which is a boutique management consultancy for diamonds, metals, and mining. And I will be talking about copper substitution. Thank you for the opportunity to speak at this conference. So I will share my screen with you. Of course, we have a disclaimer, which conveys that this presentation includes forward-looking statements, and these are based on assumptions which may prove to be incorrect in the future. And we warn against any business decision solely relied upon recommendation or forecast presented in this presentation. The antitrust guidelines for the copper industry are also clear. Now, executive summary. What happened with the copper use in 2021? Copper use has recovered in 2021, and increasingly, green drivers are increasingly dominating growth. Many copper-intensive sectors, such as infrastructure, manufacturing, or residential construction, still benefit from COVID recovery packages. The combination of strong demand and supply disruption led to increasing copper material costs in 2021. And as end users recovered and OEMs started to restock or respond to increasing the demand, they restocked more than the immediate need, driven by still ongoing supply chain disruptions and also the increasing shipping costs. They wanted to secure access to supply. So this additional restocking by OEMs led to further even increasing shortages of certain semi-finished products. The large majority of the fast-growing copper applications are impacted by green drivers such as electrification, e-mobility, energy efficiency, and high-tech. The substitution, copper substitution in 2021 is not surprisingly increased on the back of the rising copper material cost. Still, net copper substitution remained at low 1.32% of copper use. The main drivers of substitutions are obviously the copper aluminum cost ratio, but also the absolute cost difference between copper and aluminum played a significant role. Applications which experience substitution are power cables, industrial tubes, many non-electrical plate, sheet strips and foils, winding wires in transformers, and some non-critical alloy applications. On the other hand, many large copper applications like electrical plate, sheet strips and foils, building wires, equipment wires, have very limited potential for substitution, as alternative materials don't offer the performance and the requirements of these applications. In addition to this, winding wires in electrical motors experience gains as higher energy efficiency requirements required more copper and a substitution gain away from aluminum towards copper. The examples of the companies which included in the study You can see we included fabricators, cable and wire producers, end users, and also OEMs and research and development outlets. Now, 2021 was an unusual recovery year because it followed, again, unusual year 2020, which was strongly impacted by the pandemic. Manufacturing recovered in 2021. On the other hand, we expect a gradual softening of manufacturing after 2022 on the back of the rising inflation and economic and political instability. Automotive sector was weak in 2021, and this was mainly driven by the shortage of semiconductors and chips. It doesn't mean that there was no demand. There was demand for automotives, but the production could not deliver because of the shortage of components. So we expect that the global chip shortage is now set to last in 2023, and this will impact deliveries well into 2024. Construction market, especially the residential construction, was positive in 2021, and this drove short-term recovery. However, there were certain regional differences. For example, China was suffering from the Evergrande scandal, while other markets like US and Southeast Asia showed strong recovery. Infrastructure developments were strong in 2021, and they were mainly because they were also part of the COVID recovery plans, but also grid expansion, the network expansion, the installation of EV charging infrastructure. They all required copper, contributing to the infrastructure market recovery. China, still strong and leading the recovery. China recovered remarkably well after the pandemic and functioning at close to its pre-pandemic levels. The world larger copper market is fast growing and continue driving copper use in the future. As mentioned before, supply chain issues and high shipping costs impact availability in the market, and some copper semi-finished products continue to have availability issues. For example, OEMs tripled the delivery times, and it's expected that it will take 1 to 2 years to stabilize production and delivery times. The following chart shows applications, copper applications and products in a matrix. The vertical X of this chart is a future growth rate, a compounded annual growth rate between 2021 and 2026. And the horizontal X, you can see the size of the market in kilotons. On the left, smaller markets, on the right, larger markets. And the color coding is going from dark red to dark green. Dark green meaning the impact of green drivers of copper use is strong, and the dark red is the impact of green drivers on copper use is rather weak. Those applications which have a strong impact by green copper drivers are the fast-growing applications, fast-growing copper demand. So these are the other winding wires in electric motors. The WW means winding wire. Those applications which have a medium strong impact by green drivers are still fast-growing and growing applications. Applications which have a reasonable impact by green drivers are across all market size and market growth rate. And those applications which have limited impact by green drivers are the shrinking markets. So at the end, the large majority of the fast-growing copper applications are green. In terms of copper use, you can see that greenish area is a natural demand growth, mainly based on population increase and per capita income increase. But increasingly, the new copper demand drivers such as electrification, e-mobility, energy efficiency, and high-tech are driving copper use. As I mentioned before, copper substitution increased in 2021, and I just explained to you the columns. The orange part of it is the substitution loss. The blue part is the substitution gain. And the greenish, bluish part on the top of the orange columns is the loss to miniaturization. The green line is a net substitution on copper use in percentage. And as is obvious in the chart, that in 2021, the substitution increased relatively significantly, but it's as a green line shows, the net substitution is only 1.32% of the copper use. Of course, we expect that the net substitution is going to a bit further increase in 2022, but it will stabilize afterwards. The next chart is showing the percentage, and again, the orange line is net substitution and miniaturization on the copper use in percentage, and the green line is the net substitution on the copper use in percentage. In 2021, it still had 1.32% of the copper use was a net substitution. So it is still relatively low percentage. So copper substitution is happening, but it's impacting copper use only to a limited extent. Now, which copper application and products were contributing to substitution? As you can see, the first column is the distribution of copper use across different copper products. The middle column is the distribution of net substitution. And the third column is the miniaturization, distribution of miniaturization. Maybe we just focus on the middle part of it, the net substitution. As you can see, the largest part of the column is alloys and other products, which is a bit middle blue, the power cables, the dark blue, and the gray copper tube section and the telecom and data cables. These were those copper products which contributed most to net substitution. Now, what are the drivers and inhibitors of substitution? As mentioned before, relative and absolute material costs are the key drivers of substitution. And of course, copper materials costs were at historic high in 2021, and accelerated substitution where it was possible. In some applications, substitution is just simply not possible, and the price sensitivity of substitution is relatively low. The higher weight of copper is a factor in substitution, especially if the weight is relevant for the application, because of general weight, but also installation. Lighter material leads to lower installation cost. On the other hand, weight has to be analyzed in the context of it. So if the weight of copper is only a small percentage of the total weight of the product, then weight is the importance of weight as a substitution driver is relatively low. Theft is a key factor, as it applies across all geographic regions, and especially applies to copper applications which are easily accessible and use a large volume of copper, for example, power cables and even cladding. For copper power cables, this also applies to underground cables. Now, on the other hand, we have inhibitors of substitution. For example, the key of this is copper conductivity, space performance together. So as appliances are becoming smaller, the alternative materials are struggling to provide the conductivity and the space performance. So taking in a smaller space to perform the same specs compared to alternative materials. Also, energy efficiency requirements, as I mentioned before, especially in electric motors, limit the use of alternative materials in winding wires. For example, higher energy efficiency like IE3, but even more IE4, are difficult to be achieved with aluminum winding wires. Building and fire safety standards are also key. And copper's high melting point, together with the high conductivity, makes it as a material of choice for building wires, equipment wires, and critical power cables. Building codes and standards enforce this technical preference and significantly reduce the possibility of substitution. High corrosion, friction, and fire resistance of copper alloys is also a key inhibitor of substitution, as alternative materials just simply can't offer the specs. Here, substitution is ongoing, but very, very slow. As I mentioned before, the copper aluminum price ratio, a key driver of substitution. Just explaining the slide, the blue surface or line is the copper aluminum price ratio over time. The orangey part of it in the lower right-hand corner is the copper steel rebar price ratio. And the red line is a net substitution in kilotons. Probably you remember presentations from last year where the correlation of these two lines, especially the price ratio between copper and aluminum net substitution, was highly correlated. Now, this year, we experienced something relatively unusual, where the copper aluminum price ratio has declined. And this happened because not only copper price has increased, but also the aluminum price has increased. But at the same time, net substitution has decreased. So we were asking ourselves, what was the reason for this? What is the reason for this discrepancy? And also talking to a market, we discovered that the main reason for this is that not only the copper aluminum price ratio is considered by OEMs, but also the absolute price difference. And as you can see here, the blue line at the top is the copper LME cash settlement price, and the gray area and the top is a gray line is aluminum cash settlement price. And the difference between it, which is colored here yellow, is the absolute copper aluminum price difference. And this significantly widened in 2021. Now, just going back to a more overview of the applications, the matrix shows you on the vertical X the net substitution loss as a percentage of copper use in 2021. On the horizontal X is the expected future annual growth rate of copper use between 2021 and 2026. And the bubble size is a copper use in 2021. As you can see, the largest copper products, or the copper products with the largest copper use, which has the largest bubble, are in the part of the matrix which is characterized by growth and also lower substitution. As you can see, power cables, building wires, electric and electrical plates, sheets and foils, winding wires for motors, and so on. So growing markets, these are the growing markets, and combined with a relatively low net substitution. Thank you very much for your attention.
My name is Luis Gerard. I am the president of Bohn de Mexico. We are a company that manufactures refrigeration equipment and AC components. Thank you to the Copper World Conference for inviting me, and thank you, Krisztina, for inviting me to be part of your presentation. Our company consumes 3,300 metric tons a year of copper tubing and over 500 metric tons of aluminum tubing. My presentation is basically going to try to describe the drivers of the industry in the near future. In the AC and refrigeration industries, we are expecting to have copper tubing growth between 3 and 5% in the US and between 5 and 8% in Mexico. The second driver is the rate of aluminum substitution, the cost of materials and new refrigerants, and nearshoring of production. The expectations in the air conditioning industry is that growth will continue, and especially in the city of Monterrey, it's going to be a big explosion. Rate of aluminum substitution will accelerate due to the lack of supply of local copper manufacturers, cost difference between copper and aluminum, and the technology advancement in the manufacturing of aluminum components. New refrigerants like CO2 will support copper usage in the future, and nearshoring of mini-split production, especially in Mexico, will also increase the copper need. In the refrigeration industry, the expectations are the market is going to be stable and growing. In the supermarket and food industries, in the food services industry, will continue and will revive in the next 2 years. The rate of aluminum substitution will be reduced and is only threatened by the lack of copper tube capacity. New refrigerants like CO2 and propane support copper use over aluminum. Nearshoring in Mexico of important players in the refrigeration industry are commonplace. Other consideration, microchannel has set its position in the AC industry and will be less prevalent in the refrigeration industry in the future since it is not repairable, and that's a big issue in Latin America. CO2 and propane will accelerate and will make us move to smaller diameters, favoring copper but with a lower weight per unit. Logistics and labor shortages are pushing relocations to Mexico, causing a lack of copper tubing capacity becoming a concern. Thank you very much.
Good afternoon. I am John Connor with SAI Industrial, an international market research firm analyzing various industries, suppliers, customers, key value chain participants, as well as downstream markets. We have done approximately 60 projects with ICA over nearly 30 years. And recently we're asked to conduct research into the power cables market, particularly for copper consumption, and did that work earlier this year. And just to start off the presentation, wanted to also say that the following guidelines that the Copper Industry Trade Association meetings abide by have all been followed by SAI as well during the course of our research and work for this project. With that, I wanted to take you into the research that SAI has developed for power cables in new and emerging markets. We have shown overall power cable demand beginning in 2021 and increasing through 2040 from $149 billion to $350 billion. The power cable market growth has been shaped in part from new technologies for aging, transmission and distribution networks, grid modernization, as well as numerous regulatory policies and practices currently being established, particularly in the US in 2021, the rejoining of the Paris Agreement, and the goal to reach 100% carbon pollution-free electricity by 2035 has been a major impact on this future growth. Other regions as well, Europe and China, are also enacting various initiatives and policies to help promote this. In 2021, the overall global power cable market has been estimated at 8.7 million metric tons in volume terms, of which copper comprises 54% of that overall demand. The increased demand for electricity, coupled with population growth, urbanization, rising trends in renewable energy generation, replacement of older grid structures, the switching from overhead lines to underground lines will all be key factors driving growth moving forward. In 2021, China was the leading consumer for copper in the power cable segment, with 57% of the overall portion of that segment at 4.7 million metric tons. North America and Europe made up an additional approximately 13%. So those three regions alone comprised 70% of the overall market for copper consumption. In terms of market development, the move towards cleaner, renewable forms of energy includes several key areas. Solar power with PV cables, wind power for both offshore and onshore applications, ground wire and cable use, cables from towers to pads, as well as electronics and data transmission cables are all key factors. The increased demand for electric vehicles and charging stations, pads, charging points, cable assemblies, and cord extension sets will also play a role in this. And then new emerging technologies overall for smart cities, transportation mobility, energy, infrastructure, smart buildings, and data centers are also going to be key drivers moving forward. In terms of overall copper power cable demand, the global wind electricity systems installation is expected to reach nearly 3,000 gigawatts through 2040, with China being the world leader in wind installation, reaching nearly 1,400 gigawatts in that time period, followed by Europe at nearly 600 gigawatts. Of that, copper consumption is anticipated to reach over 6 million metric tons through that time period. In terms of solar electricity systems installation, capacity is expected to reach nearly 6,000 gigawatts through 2040, with China again expected to be the overall world leader with over 2,000 gigawatts, followed by North America at about 1,250. In terms of that, for copper demand, likewise, it's also expected to reach over 6 million metric tons through that time period. For electric vehicle charging ports are expected to rise quite exponentially from 3.2 million in 2021 to over 150 million through 2040. China will be the global leader in electric vehicle charging port infrastructure development, reaching up to 145 million ports by that time, of which copper demand is expected to reach nearly 1 million metric tons through 2040 from its current use. Overall, key elements include for emerging copper power cable market drivers, smart grids, energy storage, and data centers. There are significant economies of scale involved in power grid construction and development, and this has brought a huge demand and innovation to the cable industry. The modernization with automation of grids is expected to help drive this overall copper consumption. Likewise, for energy storage, market drivers include energy independence and security, smart grid investments, time of use and peak demand rates, growth in renewable and distributed generation, as well as government policies, incentives, and other regulations. For data centers, large data centers and hyperscale data centers will be the future for data storage in response to rising edge computing, smart cities, and increased use of smartphones and digitization. The increased demand for data centers will lead to infrastructure network expansion, which in turn helps drive the overall copper consumption in these areas. As part of these emerging trends, there are two critical segments, including building and construction and smart cities. Smart building adaptations will help lead to overall copper consumption, as well as the global demand for copper in climate-related commercial retrofitting markets in response to the growing adoption of green energy technologies, cogeneration, including heating and cooling efficiency, lighting efficiency, building envelopes, and so forth. In terms of smart cities, Asia and Europe currently lead the world in copper demand use at 40 and 35% respectively. By 2030, North America expects to have the highest growth and be on par with Asia and Europe in that area. The arrival of 5G networks has also increased the reliance on some key components significantly, especially connectors and cables used in wireless and infrastructure and wired infrastructure. Key sectors, though, include transport, mobility, energy, infrastructure, and smart buildings, which all use copper. And as the adoption of new copper-based technologies increase, our forecast shows copper demand in smart buildings will be a large growth area. So for these emerging technologies, such as building and construction, renewable energy, data centers, and electric vehicles, these will all be drivers for the overall copper demand moving forward. Building and construction and renewable energy segments will be expected to help really drive the overall maximum growth amongst all these areas, leading to overall 8.7 million metric tons by 2035. The copper demand for power cables is expected to reach 8.7 million metric tons with a growth rate of 4.5% annually through 2035. In conclusion, as a result of these market drivers, copper consumption will outpace aluminum consumption through that time period. That's the end of the presentation here. Thank you for the time, and I look forward to the Q&A portion of the discussion going forward.
Hello, everyone. It's a pleasure to be speaking at the World Copper Conference 2022. My name is Luke. I'm a principal analyst at IDTechEx, and I'm going to be talking about copper use and demand in the automotive market. These are the antitrust guidelines for the copper industry. And before we begin, I'd just like to take this opportunity to introduce everyone to IDTechEx. So IDTechEx is a market research company that provides clarity on technology innovation. I lead the electric vehicles research at IDTechEx, which closely ties into some of the other topics you see on this slide, like energy storage or energy harvesting. But we have a wide analyst team that covers all the topics that you see on this slide, writing off-the-shelf market research reports. We provide a constant stream of analysis with our online portal subscriptions. And we can also offer bespoke consultancy projects, which you can learn more if you visit www.idtechex.com. So please visit if you wish to know more. Now, the focus of my presentation today is copper use in the current and future automotive market. So this looks at three core areas. So that's traditional internal combustion engines, where you historically have had quite a lot of copper in the wiring loom, but also small motors like the starter motor or motors for other luxury features on the vehicle, and the alternator as well, which charges the battery, the low voltage battery from the engine. Moving forward, we're currently in a position now where electric cars are going through their exponential growth phase and are really starting to take off, and we think will start dominating the market within the next decade or so. And this really brings a lot of new fresh sources of copper demand to the automotive market, particularly in the lithium-ion battery, but also in the traction motors and the power electronics. And we've looked across copper intensity across battery electric, hybrid and fuel cell powertrains here. And then perhaps something that's a bit more into the future is autonomous cars. This is also an area that we've looked at extensively. It's one that's a bit more around the corner, and we expect to start emerging this decade and then truly starting to accelerate and take off next decade. But this also brings new copper to the vehicle in the sensors that the vehicle requires to sense its environment, and also the cabling that needs to connect those sensors up to the computer that processes all the data. Our copper demand forecasts ultimately depend on our car market forecasts, and I'm showing two different versions of that forecast from IDTechEx on this slide. On the left-hand side is our forecast by powertrain. So this includes internal combustion engine vehicles, battery electric vehicles, plug-in hybrids, strong hybrids, and fuel cells. As you can see, we're really predicting that battery electric vehicles are the winning powertrain technology over the next 20 years. And that's ultimately because they achieve the lowest emissions for the most reasonable price. And their growth really drives a decline in internal combustion engine sales through 2040. Plug-in hybrids and strong hybrids, we think, will have a smaller role to play in the automotive market moving forward over the next 10 to 15 years. That's mainly to help act as a stepping stone technology to meet emissions regulation, but ultimately they are still polluting at point of use, and we think they'll be phased out the market. And then finally, fuel cell electric vehicles do have a small presence in our forecasts, but ultimately we don't think there'll be a winning solution for the automotive sector, mainly because although they're zero emissions at point of use, their upfront cost is very high, at least comparable to battery electric vehicles. But also, I think the killer is really the expensive cost of deploying the hydrogen infrastructure, and then the cost of the hydrogen itself, which just really makes from a TCO standpoint, fuel cell cars very unattractive. Looking at our forecast split by levels of autonomy, on the right-hand side, we move from level 2 autonomous vehicles through to level 4 autonomous vehicles. And the level 2 autonomous vehicle, these types of car currently exist on the market. So they include features like automatic emergency braking or lane switching assistance, that sort of thing. And over the next 5 years or so, we think level 3 and then level 4 vehicles are going to start ultimately to emerge on the market and start having an impact on the automotive market too. So level 3 vehicles would be a vehicle that can drive itself autonomously on a highway, but you'd still need a driver to pay attention and take over if needed. And there are some models that have started to come on the market this year, like the Honda Legend in Japan. But the level 4 vehicle is essentially what you'd think of as a fully autonomous vehicle. Under most conditions, it doesn't need a driver. And so this is the situation where you could start to have a robo-taxi business model, for example, that doesn't always need a driver behind the wheel. And it's the emergence of these types of vehicle that we think are going to create new business models that ultimately reduce the need for private car ownership and start to help drive a peak in the global car market and a decline in sales through to 2040. So where is copper in today's conventionalized car? Well, as you can see from the pie chart, most of it is actually found in the wiring loom still. So that's about 85%. And the wiring loom is just the wire harness in the vehicle that is the electrical architecture that connects all the components around the vehicle, typically at a low voltage. So everything that might be powered by the 12-volt battery, for example, and that's containing the lion's share of the copper. But you also have sources of copper in the starter motor and the alternator, which between them take about 9% of the 30 kilograms of copper. And then there are also many small motors throughout the vehicle, which we show a summary of in this bar chart here. And this can be things like electric windows, which are started out as a luxury feature, but are pretty much standard in cars today. But moving on towards more luxury features, like you might have a moving seat or an electric sunroof, that sort of thing. And each degree of freedom that something needs will need one additional motor. So an electric seat that moves up and down and sideways and back to front will need 6 motors in it. So although there's a small amount of copper in each of these motors, when you have 10 to 20 per vehicle, it all starts to add up. And you get to about 3.6% of the share of the 30 kilograms. Moving on to electric vehicles, the big 3 focuses of innovation in an electric vehicle tend to be the lithium-ion battery, the power electronics, so the inverter and onboard charger, and then the electric traction motor, which is shown on this slide. And in this presentation, we'll be looking at the motors and the battery in a bit more detail. But every electric traction motor typically has copper in its stator. So that's for the 3-phase windings in the stator that help the rotor to move. Where the copper intensity differs between the different motor types tends to be on the rotor material. So currently the market is converging on permanent magnet motors, and that's because of their power density and efficiency advantage. But this on the rotor side is simply just magnets embedded or banded to the outside of a of silicon steel material. Where copper intensity does increase is in induction motors and wound rotor motors, because they have a presence of copper on their rotors here. So the yellow bars show where the copper would be on the induction motor. And then the wound rotor motor is essentially an electromagnet instead of a permanent magnet on the rotor, which allows more precise control of the magnetic field. So as I just mentioned that the market had been converging on permanent magnet motor designs, the main ingredient to permanent magnets is neodymium oxide, and we have been seeing some price volatility here. So while a couple of years ago the price was about $50,000 a ton, in the recent year we've been seeing this climb to about $240,000 a ton. And as the electric vehicle market is still at quite a critical time in terms of trying to reduce overall costs, this is something that OEMs might want to looking towards mitigating or avoiding. And a good example of that has been BMW's indication that they might be moving towards an WRSM motor design in their 5th generation electric drivetrain. So they'd join the likes of Renault, who've been using a WRSM motor in their Zoe for quite a while now, and Audi, who use induction motors. But overall, if this becomes a wider trend, this is something that would increase copper demand in the automotive industry and would be positive for copper. Looking at how copper content varies in motors across the different types of powertrain, you can see from this chart that a strong hybrid tends to have about 10 kilograms of copper from the motor, compared to pure electric vehicles and plug-in hybrids, which tend to have between 6 and 8 kilograms. The main difference in the copper content by the powertrain is to do with how many motors there are on each vehicle type. So a strong hybrid that doesn't plug in, tends to more typically have 2 motors, one for traction and then one for the regenerative braking or auxiliary systems. Battery electric vehicles also have a slight edge over fuel cells and plug-in hybrids because on average they tend to have, they're much more likely to have a dual motor configuration as well, compared to single motor configurations for fuel cells and plug-in hybrids. Moving on to copper use in lithium-ion battery packs. So as you can see from this slide, there are mainly two sources of copper in the lithium-ion battery pack. And that is on the cell side, and that is on the pack side. So on the battery cell side, you have copper on the graphite anode as the current collector. And on the battery pack side, you tend to have copper in cabling that might be used to connect up the BMS and bus bars to make the electrical connections within the pack itself. But as we show on this side, most of the copper by weight at the pack level is actually down to the battery cells themselves. So any trends that happen here will have quite a large impact on the overall copper demand from batteries in the electric vehicle industry. And while there are some trends like thinning current collector coils, like thinning current collectors moving from 10 microns and trending towards 5 microns, for example, we don't see much risk of substitution for copper here because, for example, aluminium being used at the graphite anode doesn't work because at low potentials it alloys with lithium. So copper has some specific material advantages, which is the reason it's used at the graphite anode, and we don't see that changing anytime soon, even with a shift between chemistries. And speaking of the difference in the different types of battery chemistry, here on the left-hand chart, we're showing the different types of cathode that are typically used for electric vehicle batteries. So you have your NMC variants, your NCA, your LFP. And in most of them, they all tend to have a typical similar level of thickness of the coil, of the foil, sorry. And so what happens is for the greater energy density cells, you tend to have a slightly lower copper intensity because of that greater energy density with a similar thickness of foil. So that's your NMC and your NCA variants, while a lower energy density chemistry is going to have a slightly higher intensity of copper. So we are seeing most of the market converge on high nickel and high energy density chemistries. But there has been a slight resurgence of LFP, mainly because of its less critical raw materials, lithium-ion phosphate, as compared to nickel, manganese, cobalt oxide, where nickel and cobalt have been known to have volatility in their price and supply chain issues. But from the pie chart on the right-hand side, you can see that the copper foil makes about 8% of an NCA cell in the material breakdown by weight. Looking at how we expect these chemistries to evolve over time, on the cathode side, we expect NMC chemistries to dominate and gradually for the market trend towards higher nickel versions of NMC to continue over the next 5 to 10 years, ultimately culminating on NMC 900. On the anode side, we are expecting a trend towards increasing amounts of silicon in the anode, again to chase the energy density and improve range for the vehicles. So both of these trends impacting energy density would, assuming no other changes to the copper foil, decrease copper intensity in the battery itself, in the battery cell itself. And then some of the more further reaching trends in lithium-ion batteries like lithium metal and solid electrolytes, we don't expect these technologies to truly be commercialized until the end of this decade. And even then, they'll have quite a small impact on the automotive market because of their price premium. They'll be more applicable to other sectors because of their unique advantages. For example, lithium metal increasing energy density, but coming at quite a big price premium, will be more applicable to the aerospace or drone industry. Moving away from electrification and onto autonomous vehicle trends, the main difference between an autonomous vehicle and an electric or a normal vehicle is the additional sensors required for the vehicle to map its environment. So that is normally a number of radars, lidars, and cameras. And there are different approaches. So for example, Tesla used a camera and radar system. Now they're completely ditching radar and just using a predominantly camera-based system, and all the technology innovation is on the software and computer processing side. But other companies like Waymo or GM Cruise, they're using a combination of the sensors, so radar, LiDAR, and camera, which helps with things like redundancy, particularly if you're going after a level 4 robotaxi as your end game. So the copper is found in the PCBs in the sensors themselves. The additional wiring that needs to connect the sensors to the computer and within the vehicle, this can typically be quite long because these sensors are often on the extremities of the vehicle because they need to be able to see outside the vehicle. And in the PCB of the central computer that processes all the data and controls everything. So naturally, as you go up the levels of autonomy, and you reduce your reliance on the driver, you tend to require more sensors to add redundancy and to add the capabilities needed, which means that you're adding more copper. So for a level 2 vehicle, we're going from under 1 kilogram addition per vehicle, but all the way up to a level 4 vehicle where we're just under 3 kilograms addition for all the additional radar, LiDAR, cameras, and so on. And then the main difference between a level 4 private and a level 4 robotaxi is we expect a level 4 robotaxi to require much more sensors because there will never be a driver involved, or very, very rarely, compared to a private vehicle where the owner, you, are probably going to be in the vehicle and be able to take over if needed. And that means there'll be a lot more sensors in the robotaxi, which corresponds to, again, more copper. So about 5 kilograms of copper in total for the level 4 robotaxi. And then finally, just bringing everything together. So at the start of the presentation, I showed the amount of copper in a traditional car, which was at about 30 kilograms. This is showing the amount of copper in an electric autonomous car in 2040, which we put at about 73 kilograms. Now, while a lot of that copper is still coming from the wiring loom, which is also in the traditional vehicle, over half of that copper is now also coming from the electric powertrain, particularly the batteries and particularly the motor, and also a smaller amount from the inverter, with about 6% coming from the autonomous vehicle, sensors and computers and PCBs as well. So this is accounting for a relatively sensor-heavy autonomous vehicle, so more equivalent to a robotaxi than a private level 4 vehicle. But this is accounting for 12 cameras, 7 LiDARs, 8 radars, and then the central computer controlling everything, as well as a over 100 kilowatt hour battery and a roughly 200 kilowatt sized motor. And applying this to our car demand forecasts, which I showed at the start of the presentation, you can yield the total copper demand that we're expecting from the automotive sector. And as you can see, in 2020, we have a prediction of about 2.4 million tons of copper from the automotive sector, with most of that being attributed to the wiring loom. But as we go through to 2040, the growth drivers are coming from electric vehicles, particularly the lithium-ion battery and the motor, as well as autonomous vehicles, which have a smaller, roughly 6% share in the later years, to yield a total of 6 million tons by 2040. And with that, I'd like to now hand everything back, and I look forward to discussing this more in the panel discussion and answering any questions. Thank you.
John, and Luke. We've now got a few minutes for question and answer, and also we'll have a chance for the audience to chime in. I want to first and foremost thank everyone for their great presentations, really some great information there to really dive into. I want to start with Krisztina. Krisztina, can we talk about how you think the recent political and economic instability may impact copper use when you look at the rest of 2022?
Ernest, thank you very much for this question. It's not an easy question to focus because we can't see. Can you hear me?
Yes, yes, yeah.
Yeah, we can't really focus how this situation will play out in the future. It will have a positive impact and a negative impact, in my view, on the copper use. And the positive impact is, of course, some additional application, as additional use. For example, from the political instability, the ammunition use is extremely increased in the past, but it will have also a negative impact on consumer demand and the confidence in the economy. So in my view, and also additionally, the green drivers will continue having an impact on copper use. So I assume at the end, we will have a positive impact on the copper use, but not because of the economicals and the political instability, more because of the green drivers still working on and impacting copper use.
And when you look at the projections for green penetration over the next, let's call it 6 to 12 months, with that political and economic stability baked in, do you see the green revolution being slowed down at all, and thus copper demand from the green sector? Or how would you sort of rank it contrasted with this instability that we're seeing?
The Paris Agreement is completely independent from the political and economical instability. What is going on? Governments have committed themselves to decarbonization, carbon neutrality by 2050, 60, and 70. And this can be only achieved by renewable energy. And this has an impact on copper use in generators, inverters, power cables, e-mobility in electric vehicles. It has an impact on winding wires in motors, on automotive wiring, charging infrastructure, and energy efficiency. Again, winding wires, motors, and the electrification with grid expansions and transformers. Again, it has a positive impact on copper use. So this continue having an impact on the copper use and positive impact on the copper use. And I don't see this going to be impacted by the political and economic instability in the future.
Gotcha. Thank you. Louise, I would sort of pass the same question over to you if we could get your thoughts on how recent political and economic instability may or may not impact copper use in the spheres that you look at.
Well, thank you for the question. I don't think, I'm a little bit in line with Krisztina. I don't think the political or the situation affects the copper consumption in our kind of business, which is basically the copper tubing. We're more dependent on the residential growth in our markets. So the more houses that are being built with needing air conditioning or refrigeration, we get to more business. So I think it's more related to the economical growth. So if this political situation affects growth in the main economies, it will certainly affect the copper consumption.
Gotcha. Great. Thank you. John, I want to turn to you now. Can you talk a little bit about some key factors resulting in growth for copper demand and power cables in the future? What are some things that you look at when you look out the next 6 to 12 months?
Yeah, okay. Thanks, Ernest, and appreciate the question. Obviously, with the increased just expansion of the population and the need for the growth in renewable energy generation, we see a lot of opportunities there, particularly for replacement and upgrades of existing and aging grid infrastructure, where copper will certainly play a role there. With the rise of smart cities and smart grids development, there's going to be development there as well. We've talked about e-vehicles in the future, certainly in China, as well as in Europe, and then eventually here in the US, where I'm located. That's going to be an increasing demand opportunity as well going forward. So there's going to be some significant growth and opportunities there going forward.
And John, when you look at regions around the world, we're obviously historically used to thinking of China as a huge demand driver for copper. Talk about specific regions that you're looking at that either could be pluses or minuses on copper demand growth.
Well, China is certainly going to be the leader in this area going forward, as our research has shown. They're about 57% of the current copper demand in these types of areas going forward. We have Europe and North America for an additional about 14%, Europe about 10%, and North America about 4%. And then the rest of the world collectively, and that includes Latin America, the Middle East, and the rest of Asia Pacific, including India, Australia, and other Asia Pacific countries. But those big three regions, China, Europe, and North America, are contributing about 70+% of that growth going forward, and we expect that to continue.
And can you talk a little bit about how you bake those numbers together, sort of the methodology that you use to pull all that? And I would sort of add maybe a part B to that question. I think there's been some concerns that China's copper demand might be slowing down in sort of the recent past, but you expressed sort of a bullish, if not optimistic view, certainly on Chinese demand. So could you talk about sort of the raw data behind how you arrive at that confidence?
Sure, and thanks for the question. The basis of the research that we did for ICA in this current study was primarily based in Europe and North America. We did do interviews into China for that information. We spoke with power cable manufacturers, metal material suppliers, in addition to ICA, other associations knowledgeable in the market, such as International Renewable Energy Agencies, the International Energy Agency, Europa Cable, and others. And then along the way, speaking to them to get beyond whatever has been publicly published, to get some additional insights into the feedback that we've been developing. And that's been the basis of the work that we've done throughout the years, is to help supplement the information that's published publicly, and then to dig into some of the additional details going forward.
So sort of last question on this, John, but if folks express sort of a hesitation or had expressed in the past about Chinese demand, it sounds like you would say that from everything you're seeing on the data, that it's not necessarily a giant worry as things stand today.
Well, I think it's still, they're going to be the leader in this development and the driver for future copper demand and consumption going forward. Clearly, from their overall industry, and their growth objectives, that's where the focus is going to be. They're really driving that segment going forward.
Gotcha. Great. Thank you very much, John. Luke, I'd love to turn to you now and talk a little bit about EVs and autonomy. Thanks for your presentation. Got to start right at the top with a question about how real all of this is going to be. Certainly, you presented a lot of great information and data for us to digest, but the thought of my car driving itself still petrifies me. I can barely drive it myself. So is autonomy really going to happen? And if it is, what are some of the main barriers for us to get there?
Yeah, thank you. That's a really interesting question. And I always think back to kind of around 2015 when, all the players that were kind of developing autonomous vehicles all said that we'd be driving them in 2020. 2020 kind of came and went, and here we are 2 years later, still not really driving around in them. So I think it's really difficult to predict when autonomous vehicles are going to come to the market, just because OEMs have been so wrong about their predictions. But what we're currently seeing happen at the moment is the emergence of level 3 vehicles. So that's the vehicle types that can drive themselves on a highway, but still need people's kind of mind to be on the road. And that's something where the barrier has really been regulation so far. So it's a circumstance where we've had kind of the technology ready, but the regulation has been limiting the uptake. So the main kind of pain point there that's now been solved has been who takes ownership of kind of what happens in an incident and who has liability. But we've seen Mercedes and some OEMs start to signal that they'd be the ones that take liability, and that's helped ease some of the regulatory barriers. But in terms of level 4 autonomy, so at the beginning of the year, we had GM say that they're expecting this by mid-decade. I think we're currently predicting that level 4 autonomous vehicles would be emerging in higher volumes kind of after 2030. And this would have quite an impact on the overall automotive market. It's one of our main drivers for kind of our peak car scenario, because we start to get to the point where you have an autonomous robotaxi becomes a bit more economically viable than owning a private car. So that's the assumption behind that. But in terms of copper demand, this doesn't affect it as much because you have growth in average battery sizes where a lot of the copper is. You have growth in sensors per vehicle. So you get more of a flat response in copper demands as you get a rise in level 4 autonomous vehicles.
Gotcha. You talked a little bit in your presentation about how Tesla has moved away from LiDAR and radar, but others sort of maybe have not taken that yet. Do you expect Tesla to be the leader here and this to spark a wider trend, or do you sort of expect this bifurcation to grow?
Yeah, again, that's really an interesting situation. And it's kind of, Tesla seems to be the odd one out, as usual, as with in many of the kind of powertrain technologies they cover.
And I think happily so.
So, yeah, I mean, I think what we're predicting is that an autonomous robotaxi would need a lot more sensors for the redundancy side of things. So I think the wider trend would tend towards having more radar and more LiDAR. I think Tesla's logic is that if you have eyes and you personally can drive, then why can't a camera do everything? But I think the problem with that is we want autonomous vehicles to become safer than human drivers, not just to equal it. And so that's going to be something that radars and LiDARs can help do. So in terms of kind of how copper demand varies between the sensors, it's more about the wires connecting the sensors and the PCBs in the sensors. So it doesn't particularly matter if you have a different types of sensor over the other in terms of copper demand, but it's more about the number of sensors, and we think that will be increasing moving forward.
Gotcha. So we've talked a little bit about autonomy, Luke, and now we've talked a little bit about sort of the sensors and the hardware behind it. If I'm sitting in the audience here at the World Copper Conference and I'm thinking about, okay, these different technologies, how should I be thinking about the implication for copper demand as these different technologies evolve? And what would sort of be your baseline message to the audience right now? Is autonomy and LiDAR and radar use going to, surge a demand in copper, or is it just going to be a cool little sort of add-on to the cars that will, help me drive better?
Yeah, so there's definitely a positive impact for copper. It's just lower than electrification in terms of autonomy. So autonomy, we're predicting about 6% of the demand by 2040 will be from autonomy, and compared to the electric powertrain, which mainly the battery, mainly the motor, that's going to be over kind of 50%. So as autonomy develops, as I said, we'll get more sensors, we think, and that will increase copper demand. As other powertrain technologies develop, generally, as I said before, we're trending towards larger batteries. That's going to have a really kind of big impact on overall copper demand. So I think the message really, I suppose, is that yes, these trends will lead to an increase in copper demand per vehicle.
Gotcha. Great. Thanks, Luke. I want to toss it open to our panel itself. You guys come from several different areas across the economy and the copper space. Do you have questions for each other? Krisztina, maybe for Luke, or John for Luis, or vice versa? Someone must have a question. If not, I'll jump in, and nobody wants to hear me keep talking. All right, well, I'll maybe, Luis, you were talking about sort of home use for a lot of equipment and whatnot, and Luke is talking a lot about autonomy. I think sort of the holy grail for a lot of different OEMs, automakers, is, EVs that are charged at home at night and what that means for sort of you have solar panels on your roof and then you're charging your electric car in your garage, for instance, or nearby on the street. Presumably that, how can I ask you both, how do you see that trend taking off? And certainly if it's a large adaptation or adoption, excuse me, that would involve a lot of copper demand, I would imagine. Go ahead, please.
I have one question that now that I'm being, what's the impact on in the motor side with the technology that is coming about of the electronically commuted motors that are replacing the traditional shaded pole motors? I think that replaces a lot of copper consumption, and I don't know. I'm not so sure how much of the total volume of motors is going to be replaced with electronic commuted motors. So I don't know if
that might be for Luke.
Yes, that will be for Luke.
So yeah, in electric traction motors, which has been kind of one of the big sources of copper demand, we are seeing some kind of switch to aluminium in some of the secondary motors in the electric vehicle, but that's mainly the secondary motors that are for kind of the ludicrous mode and for the extra performance. In the core motors, we're not seeing that shift. I think a larger driver or a larger concern here is perhaps more going to be on the shifting away from permanent magnets rather than shifting away from copper, because that's where a lot of the volatility and kind of supply chain and sustainability issues come in for motors. So that's what we're seeing there.
Okay, because in our industry, we saw a big trend of moving away from the winded motors to electronically commuted motors. They're more expensive, but they save a lot of energy. And so for the cost savings on the use of the motors, and now with all the supply chain problems, we see that like a trend back into the traditional winded motors.
I don't know if you have any thoughts or reaction, Luke, or?
Yeah, so I haven't seen any kind of big changes to the way motors are operated within the vehicle itself on the traction side. So it's pretty much been standard radial flux operated with three-phase inverter for most of the market that I'm aware of. So I haven't seen any big changes there.
Okay.
Thank you, Louise and Luke. I have a question for Krisztina. Can I ask is minimization good for copper? Things are getting smaller across the board, including my iPhone. Is that good for copper demand?
Generally, it's good. Miniaturization. Now, miniaturization can happen for different reasons. As you mentioned, your iPhone is getting smaller. So all electronic products are becoming smaller. Therefore, all the components within these products are also becoming smaller. So, and very often these components are not subject of substitution because they are electrical components. There are other applications, for example, where innovations are coming in. For example, the industrial tubes, the smaller diameter industrial tubes in air conditioners and refrigeration keep the position of copper. So miniaturization is always a better solution for copper than substitution. And OEMs, if they can miniaturize copper components, then they would rather go for this as opposed to use a completely different material with a completely different technology and production line is required. Interesting example, the permanent magnet motors, as also Luke mentioned, use around 20–30% less copper than the traditional electric motors. But there's also a trend where the copper content of alloys is declining. If that technology or if new alloys can provide the performance with lower copper content or maybe better performance than previously, then this is also a trend in miniaturization in the alloy field.
Thank you very much. Luke, just jumping back to you, are there any factors which might slow the adoption of EVs? I know that's a wide question, but I'm gonna toss it over to you.
Yeah, it's a really good question. I mean, at the moment, the automotive sector is facing kind of unprecedented challenges kind of from all sides. From the battery side, I suppose, at the moment, there's concern around the lithium shortage, which is emerging over the next 2-3 years. For the wider industry, there's also the chip shortage, which Krisztina mentioned in her presentation, but it's still lasting and it's going on. I think what I will say is kind of everyone thought that in 2020, the COVID-19 pandemic would stop or slow down growth of electric vehicles. But electric vehicle sales have been surging over the past 2 years to 6.5 million sales last year, kind of almost doubling in growth. So I think, there's a massive government push. Consumer awareness is stronger than ever. OEMs are really getting behind this now with more and more targets, and there's just huge demand. So there are these huge challenges, but we're still predicting electric vehicle markets to keep growing. Yeah.
You mentioned lithium, Luke, and that reminds me that there's some concern that rising lithium prices could affect EV demand by pushing up the end price for the consumer. If copper prices were to rise exponentially or much higher, would that have an effect, do you think, on EV demand?
So I think, I suppose I'll just point to the fact that copper has to be kind of used in the essential places in the vehicle. So as I said in my presentation, one of the main areas it's used is the battery on the anode side, and it's really difficult to make a substitution there for any other metals like aluminium for technical reasons. And so any price increases for copper, ultimately, it'll take time to work through the supply chain, but that will eventually have to be factored in, I suppose, to the vehicle. And we have seen like Rivian raise their prices. Tesla, I think, earlier in the year had to raise their prices. And we have started to see some of these challenges come through. But as I said before, demand is still really strong. I mean, Tesla had their plans to make a 25K vehicle and forever have had plans to make a $35,000 Model 3. But they keep delaying this because demand is so high. And why would they reduce prices of their vehicles when demand is so high?
And extended on that question, and would be around the plans to expand a charging network, not only in the United States, but elsewhere. Certainly, you've got the demand for electric vehicles, which is one thing, but we've got political will behind the charging network. Do you have any modeling sort of around copper demand for that, or too soon to say perhaps, or too geographic region specific perhaps?
Is this another one for me?
Yes, sorry.
Yeah.
So you pulled the EV short straw today. So.
Yeah. So we didn't specifically look at charging infrastructure as part of this study. We have in our modeling a number of around, you need one charging station for around 10 electric vehicles, serve 10 electric vehicles. And I think we're starting to kind of get to a point where we are seeing slight bottleneck on the charging side. But yeah, we're seeing kind of strong copper demand from the charging side too. You need it in the power electronics, in the public chargers, and obviously you need it in the cable, and cables are getting thicker as you move to higher DC powers of charger. So yeah, that's another kind of large area of copper demand from the electric vehicle side.
Gotcha. Great. Well, Luke, Krisztina, and John, thank you both for your excellent presentations and for your time. I want to be conscious of the fact that we are standing between our audience and the end of the day and a happy hour. So I think we will wrap it up there. Thank you to our amazing panelists again. We look forward to being in person. Hopefully next year we will all be off virtual and together with you in Santiago. But until then, we'll say thank you and have a great day.
Thanks, everyone.
Thank you, Ernest. Thank you.
Sarah.